Hello everyone, I hope you're all having a great time at the conference. My name is Davy Ouedraogo and I'm currently a PhD student at the University of Sherbrooke in the Cobios laboratory. So today I'm going to present you a new approach to infer transcript phylogenies based on precomputed groups of conserved transcripts. So why is it important to reconstruct transcript phylogenies? We know that due to the alternative splicing mechanism, uh, eukaryotic genes can produce many different transcripts. So reconstructing transcript phylogenies will help us to elucidate many questions about the evolution of these alternative transcripts. So how do new transcripts arise during evolution? Where was a particular transcript gained or lost in the evolution of a gene family? So in this work, we propose a new method to reconstruct transcript phylogenies, but based on pre-computed clusters of conserved transcripts. So the method starts with a gene tree and a set of corresponding transcripts with a matrix distance between them. So the matrix represents the distance, the all distance between all pairs in the set of the transcript. So we have the gene, the leaves of the gene tree, and we assume that the genes evolve through three evolutionary events. So we have the speciation event derived from the species. We have the duplication when two copies of the genes are present in the same species, and also we have the gene loss when simply a gene is lost during the evolution. And the last input is the set of clusters of conserved transcript, of course. So we have a toy example here where each component, connected component represent a cluster of conserved transcript, where the nodes represent the conserved transcript as well. And an edge exists between two transcripts if and only if the two transcripts are derived from distinct genes and the two transcripts are considered a reciprocal best hits. Otherwise, if the two transcripts are derived from the same gene, and the similarity between them is higher than any other transcript. So the similarity in terms of distance that can be deduced from the matrix distance of the input. So this is the overall view of the method. So the method starts, as I said, like with the gene tree and the set of cluster of conserved transcript at the input. And the first step is to construct the autolog trees, the set of autolog trees. So an autolog tree is just a tree that describes the evolutionary history of a set of transcripts in a cluster. So autolog trees minimize the LCA reconciliation with the gene tree at the input. So LCA stands for lowest common ancestor, so LCA reconciliation. So based on the homologous relationship between genes, we assume that transcript evolved through creation and loss, and also other events derived from the gene evolution, such as the speciation and duplication represented by circles and squares, and the creation event represented by triangles. So we assume that after a creation event, the transcript tends to diverge from the original one. And the last step is just to merge all the autolog trees that obtained at the prior step. So we construct at the end a super tree. So this step is NP hard as we seek for a super tree that first that has a minimum sum of branch length first. Secondly, the super tree must have must preserve the sorry must preserve all the autolog trees at the input. And thirdly, finally, we have a super tree that minimizes the LCA reconciliation cost with the gene tree at the input. So for that, we propose a heuristic called min evalrec, stands for minimum evolution reconciliation super tree. And this is a progressive algorithm where for each iteration, we select first two trees in the pool based on their distance. And then we merge these two trees by attaching one tree to an edge of the other. And finally, we just remove the two trees in the pool and added the merged one. So the first statement can be achieved by just using the well-known neighbor joining algorithm. And the second step is just it can be achieved by just using an exact dynamic programming algorithm. So for this exact dynamic algorithm programming, we first defining our cost functions. So we have the considering the gene tree at the right, We can denote a node x for which we want to calculate, to compute the local cost of LCA reconciliation. So suppose we have in the first example, we have the node x. So if x is a creation event and the two children are the same label than x, so when I mean label, I mean the gene from which were the transcript derived. So if x is a creation and the two children derive from the same gene, then we infer a cost of 1. And in example 2, if the node x is a creation event also, and one of the children has the same label than x, has not the same label than x, then we account for, then the cost equal to 2 plus the number of gene lost in the path between the gene X and the gene of the children. So 2 is just for first for the creation event, and secondly for the transcript copy lost in the current gene. And in the third example, if X is a duplication or a speciation event, then we just count for the gene lost. So after defining our cost function, we are now able to propose our exact dynamic programming algorithm. And so this is the recurrences at the top. And the main idea is just to graph onto the tree, either to the left or to the right of a node, starting with the root and proceeding toward the leaves. So to the best of our knowledge, there is only 2 tools that are dedicated to reconstruct transcript phylogenies. So one has no source code available at this moment, and the other one use data directly retrieved from ensemble comparator database. So these tools cannot be used for comparison with our simulated dataset. So instead of that, we adapt Giga. Giga is mainly dedicated to reconstruct gene trees. So, sorry. Giga is mainly dedicated to reconstruct gene trees, but given a multiple sequence alignment at the input and also a gene tree, Giga can compute transcript tree. So we use Giga to make a comparison with our simulated dataset, and we compare the pairwise homology relations inferred by our method and also those inferred by Giga. So both methods exhibit good precision and recall. So for different type of pairwise homology relations, so we distinguish 4 types. So auto-autologs, if the lowest common ancestor in the transcript tree is a speciation, and para-autologs if the lowest common ancestor in the transcript tree is just a duplication. We also distinguish recent paralogs if the lowest common ancestor in the transcript tree is a creation, so a recent creation, and ancient paralogs if the lowest common ancestor in the transcript tree is a ancient creation, sorry. We further compare our method with Philosoft and Giga on the TAF6 gene family. So the transcript at the leaves color in the same color means that they are clustered in the same group, into the same groups, except the transcript in white. Transcript in white means that they are orphan, so they are clustered, they are unique in their clusters. So yes, considering Giga, the most at the right, we can observe polytomies that this doesn't give us any supplementary information about the evolution of transcripts. But considering the 2 trees reconstructing using Philosoft and EvolRec, our method, we can see similar trees, as Philosoft tends to construct forest as they allow phylogenetic connection between transcripts when the transcripts are similar. So the method is very stringent compared to our method that allow inferring additional phylogenetic relations. So to conclude, our understanding transcript evolution is crucial for the functional adaptation of genes and genomes. And in this presentation, I present a method, EvolRec, that demonstrates good results on both simulated data and real data set, corroborating the findings of previous studies. So in the future works, future work will consist to first apply the method on larger scale to multiple gene families first, and after we will evaluate the result with non-biological knowledge about transcript isoform functions. I would like to thank the Canada researcher, the Cobius Lab, and the University, the Sherbrooke for their support. Thank you so much.